Gelmemişler hocam.
Emin var hocam burada.
Merhaba, nasılsınız?
İyi sağ olun. Duyabiliyor musunuz?
Duyuyorum
Emin,
hocam.
Emin sensin herhalde.
Evet, benim.
Tamam. Tamam. Benim konuşmadan sonra sanırım sana geçeceğiz Emin.
Tamam.
Slaytlar değişiyor mu Emin?
Evet, sizin şu anda
Tamam.
görüyorum ben.
Tamam. Çok güzel. O zaman biz tekrar başlayalım. Buçuktan mı başlıyoruz hocam? Tamam. Okay. Okay. Now the last lecture of the row. Now, I will be talking briefly on the radioactivity, basically electron, neutron, or proton or alpha emitters. I mean, what is radioactivity first? Some basics of it, basically alpha decay, beta decay, and gamma decay will be covered with this. Now, okay, there are 92, basically, up to Z equals to 92 uranium. There are stable nuclei. Also, there are unstable ones because of the excess of proton and neutron numbers, or even the sometimes electron capture due to some instability. Therefore, in the universe, basically, A is, as you know, the sum of n plus neutron and the proton number. Therefore, A is mass number. For even A, that means even N, even Z, there are 166 stable nuclei. And for odd one, there are 8. For A equals, or, well, let's say odd ones, even odd or odd even numbers of neutrons and protons, there are 57 and 53 different nuclei. Therefore, the remaining around more than 2,000 ones are unstable, actually. Therefore, they decay, basically. Yeah, that means they are excited or unstable. Therefore, they either decay through alpha and beta, like not only the energy, but also the mass, or through the gamma rays, they became stable. Therefore, we have there are different mechanisms for this. The ones that strong force mostly for alpha decay and fission. For weak ones, mostly beta decay, beta minus, beta plus decay, electron or positron. Or electromagnetic ones are the excitation of gamma ray emissions. Now, this is the value of stability, as we have shown. This axis is the neutron numbers, and this is the proton numbers. Therefore, line of stability, Z equals N, is something like this. Now, this line, below that one, there are neutron axes. Therefore, in the heavier part, up to uranium and further, mostly we observe these alpha decays in this region. Also fission here at super heavies. Now, in this part where the proton exceeds, therefore, because of the Coulomb force between protons, there are alpha decays here at proton drip line, and also these are really deformed nuclei, like either oblate or prolate, and they have this rotation and vibrational energies. Now, therefore, each side of this valley, we observe electron, that means beta minus, and positron decays here. And gamma decay are observed everywhere where there is an excitation of nucleus. And if these are too heavy in this region, there are spontaneous fission. Therefore, these are the decays that we observe in nuclei over 2001. Now, what are the basics of radioactivity and their units, etc.? An unstable nucleus is transformed into stable ones. Therefore, unstable one is called parent nucleus, and the stable final product is called daughter nucleus. Therefore, it is a random process, very, very stochastic, very probabilistic. That's why we have this famous formula, if you remember, change of number of nucleons per time depends on the initial number of nucleons times a constant. It's a decay rate. Therefore, we obtain this formula. It works very well for almost all nuclei. Therefore, this is describe the number of unstable nucleus to stable one. The time basically passes is half-life or mean life. These are called mean life or half-life. Therefore, this is the basically explained here. This lambda in the formula is called decay constant, changing from nucleus to nucleus. T is the time, and 0 is the amount at the beginning. Therefore, 1 over lambda is mean life of the basically unstable nucleus, and half-life is given like this. Therefore, mostly in unstable or radioactivity, we will be using this half-life, basically. Activity is mostly Becquerel. We describe in the old activity unit Curie, and there is a connection between these two units. Now, of course, in depending on the branches like radiotherapy or other branches, we also use different. We develop different units like Gray or Sievert and others to describe the amount of dose absorbed. Therefore, in the, of course, decay, A decays to B, B decays to C, where C is stable. Therefore, there is a decay constant here, while the A is decreasing, B or C are increasing, of course. I mean, this is the basic decay constant. When we look at the alpha decay, basically alpha decay is like a helium nuclei. That means alpha. 2 protons and 2 neutrons we have, and mass number is 4. Therefore, when a nucleus goes through the alpha decay, mass number changes -4, as well as the atomic number changes -2. Therefore, this is like the diagram. This is X, A, Z decays to Y, A -4, Z -2 plus alpha. Therefore, it should, the baryon number should be conserved. Don't forget, the number of nucleons should be conserved. Therefore, here, for example, thorium plus alpha, 238, that 238 uranium, therefore the mass number are conserved. It is because of this, okay, yeah, I mean, first experiment, of course, done by Rutherford, alpha particle at that period, it was called alpha particle now, but we use helium-4, that's 2 proton and 2 neutron, and it's because of the Coulomb repulsion, mostly observed in this region. Therefore, now, particularly in the theranostic, I mean, mostly people use targeted alpha therapy. I mean, the most or the easiest way to produce such nuclei is to bombard heavy nuclei either excite 3D photonuclear processes or proton excitation is the best way to produce targeted alpha therapy. The Q value of the decay is calculated by delta M times C square, famous Einstein's equation, and it should be, of course, greater than 0. Now, this is a typical example of, I don't remember, I can't see it, but plutonium or similar. The idea is, as you see, there are different alpha decays. These are branching ratios, and there are different peaks, you see, for decaying. That is discrete, what we mean. Alpha decay is a discrete process. It is not a continuous process. Therefore, once a time, it decays. It's not continuous, and it changes the nuclei to another nuclei, a nucleus to another nucleus with different alpha decay energies. There are some mathematics to do such things, but the easiest way is typically emitted alpha particles have kinetic energies of 5 MeV. Therefore, if you remember third year quantum mechanics barrier problem, then you can calculate this alpha, how long it will travel in a medium. You see, this is like it could be a tumor or it could be a cancer, anything, or it can be a wall. I mean, like this. But you know the energy, you know the mass of the alpha particle. Therefore, you can calculate the transmission coefficient so that how deep it can penetrate in a sample. From energy conservation, we can calculate the Q alpha easily by the kinetic energy of daughter and alpha particle. And of course, the Q value. These are basic things, mostly probably, I mean, you don't have to use, but for an example, uranium on thorium decay with an alpha, you can calculate the energy of alpha. Therefore, it is something like 3.6 MeV, as you see. This is an example exercise for you. You can do the calculations. Now, it is observed that there is a really strong correlation between the half-life and Q value of the alpha decay. Now, if you increase the Q value in factor of 2, then you get 20 orders of magnitude in half-life. Why is it that? And what is the dependence of half-life on Q value? I mean, we can show it theoretically like this. Now, how we calculate? I mean, this is, imagine, this is, let's call it, actually, this is like a binding potential. Here, there is uranium, but there isn't uranium now. Thorium plus alpha is here. And alpha in a positive energy state. Therefore, now, if the energy of alpha is so important, because if the energy of alpha is here, for example, it will travel this much. Whereas if the energy of alpha is very high, it will transfer from this point to this point. Therefore, half-life changes because of dependence on the energy of alpha. You see, that's why very important the energy of alpha in a proton structure. Now, how we solve it? Basically, what we do is very simple in quantum mechanics. We divide this into 3 different regions. First part, like it's the quantum well potential. First year quantum physics, you see, quantum well here. Second one is there is energy less than Coulomb potential or potential. And third one, there is no potential free power. Therefore, the wave here and the wave here, it's both are free, almost free, but there is this region where there is exponential decay. Therefore, when we match them, then we obtain the properties of all the properties of alpha decay. Look how simple it is if you consider the first two lectures in the morning. This is a simple quantum wave problem in third year quantum physics, and you are doing really advanced physics. These have many applications in medical physics or everywhere in the field. Therefore, please recall this mean field potential approximation there. Now, sorry? Tamam. Okay. Yani şöyle düşünün. Şimdi alfa parçacığı, alfa bozulumu dediğimiz şey, alfa parçacığı çekirdekte önceden var oldu. Çünkü alfanın çok yüksek bağlanma enerjisi ve yüksek simetrisi var. O yüzden şimdi şöyle düşünün. Uranyumun 238 tane proton, nötron var. Şimdi bunlar böyle dağınık belirli kabuklara yerleşme yerine diyor ki bazıları biz daha kararlı olalım diye alfalar şeklinde kümeleniyor. Dolayısıyla alfa çekirdekte uranyumun içerisinde 234 toryum burada, bir de alfa var. Sonra bu alfa normalde negatif potansiyel bağlı durumdan oluşuyordu değil mi? Yani şöyle düşünün. Şimdi burada efektif potansiyeli çizerseniz şöyleydi efektif potansiyelin şeklini hatırlayın bir önceki sunumda. Dedik ki böyle bir negatif kısım var, şurada da Coulomb bariyeri var. Böyle değil mi? Efektif potansiyel. Yani ve efektif dediğimiz ve bunları kısalttığını düşünün. V nükleer artı V Coulomb artı V sentrifüj. Böyle. Şimdi bakın şurada protonlar, nötronlar böyle enerji seviyeleri Fermi enerji seviyesine kadar yerleşiyorlar. Fermi enerjisi. Ya buraya kadar dolduruyorlar. 1S1 bölü 2, 1P3 bölü 2, işte 1P1 bölü 2, işte 2S1 bölü 2, 1D5 bölü 2 vesaire vesaire böyle doldurdular. Yukarı aşağı fayda dışarılama etkisine göre. Tamam. Şimdi burada alfa kendisi yüksek simetri nedeniyle bu şekilde kendisini oluşturuyor. 2 proton, 2 nötron. Şu alfa. Şurası da toryum. Şu alfa. Bu çekirdeğin adı da aslında 238 uranyum. 92. Tamam. Şu alfa pozitif enerji seviyesine geçtiği zaman bakın sıfırın üzerinde. Bu bağlı. Bu bir şekilde buradan buraya tünelliyor ve çıkıyor. Şimdi alfanın enerjisi ne kadar düşükse bakın seyahat edeceği mesafe şurası R o kadar uzun. O yüzden T1 bölü 2 çok yüksek oluyor. Yarım. Ama alfanın enerjisi ne kadar yüksekse şurada diyelim ve seyahat edeceği yer bu kadar. O yüzden T1 bölü 2 bu kadar kısa oluyor. Şimdi nasıl formülize ediyoruz bunu? Diyoruz ki 3'e bölelim. Alfanın davranışı. Bir, şurada bağlı olduğu durum. Bu bağlı olduğu durumda potansiyel sıfır. Dolayısıyla diyoruz ki pisi 1 diyoruz. X ya da R. A, E üzeri I eksi İKX artı B, E üzeri İKX. Tamam mı? X'i de alalım. İkinci bölgede bakın oradan oraya tüneliyor. E ve sıfırdan küçük olduğu için bu K1. Ya diyoruz ki pisi 2 diyoruz. C, E üzeri eksi K2X diyoruz. İyi yok bakın. G diyor. Ve üçüncü bölge serbest bölge diyoruz. Diyoruz ki pisi 3 X ya da R artık o bir boyut şey. Diyoruz ki D E üzeri İKX artı F E üzeri eksi İKX. Sonsuzda sıfır olmak zorunda olduğu için şu terim gidiyor. Değil mi? ya da sabit olması için. Orijinde 0 olması gerektiği için bu terim mi gidiyor? Biri gidiyor, tamam mı? Dolayısıyla şu üçünü birbirine eşitleyerek alfanın o davranışın hangi bölgede nasıl bir enerjiye sahip, nasıl bir davranış gösteriyor, böyle gözüküyor.
Yani aslında bir alfanın olasılıksal olarak 3 bölgedeki dağılımına bakabiliyoruz.
Çünkü biz modern fizik yapıyoruz. Alfa şurada ya da burada diyemeyiz. Alfanın en yüksek ihtimaliyetle bulunduğu yeri söylüyoruz. Bakın. Hisi L, L, M, R diyoruz. N, yani mesela bir S dediğimiz zaman bakın bir S. N dediğimiz burada bir, S dediğimiz N eşittir 0. Dolayısıyla L'in her bir değeri, yani N, şöyle düşünün, yani 3. sınıfta yapmışsınızdır bunu. Buna complete set of commutative observables diyoruz. Yani H ile Hamiltonian L kareniz, yani H ile LZ'tiniz ve L kare ile LZ commute ettiği için siz P'yi R teta pi ya ayrı ayrı yazabiliyorsunuz ve R'yi sadece yapıyorsunuz ve burada L sistemin bir hareket sabiti. Ne demek o? Yani L eşittir 0 ise S V diyorsunuz. L eşittir 1 ise P diyorsunuz. L eşittir 2 ise D. L eşittir 3 ise P vesaire. Yörüngeler ortaya çıkıyor. Eğer siz şu komütasyonu yaptıramıyor olsaydınız, yani komütasyon yaptınız değil mi? Hx, H'ler, bunlar sınavda da çıkmıştır size. O komüt etmiyor olsaydı, eşittir 0 olmasaydı bu sefer siz L sistemin bir hareket sabiti olmalı ve böylece de bu sefer atomu, çekirdeği oluşturamadınız çünkü yörünge ortaya çıkıyor. Yörünge dediğimiz şey şu Hamiltonian'le L kare ya da L kare ile LZ komüt ettiği için siz L sistemin hareket sabit oluyor ve yörüngeler ortaya çıkıyor.
Ortak enerji aydınlıkları.
Aynen.
H için aydınlıkları,
Ortak aydınlıkları.
LZ'yle de aydınlıkları
Evet.
ortak olduğu için.
Dolayısıyla bunu yani bu zaten şartı sağlıyorsunuz. Sonra diyorsunuz ki L'nin 0 için şu potansiyel ne hali? L eşittir 1 için ne olur? L eşittir 3 için ne olur? Bunları yazın. Sonra oraya alfaları yerleştiriyorsunuz ya da herhangi bir şey. Orada bu pozitif enerji durumuna geçti diyelim. Hangi bölgede yüzde kaç ihtimalle orada? Onu buluyorsunuz. Yani %100 dışarı çıktığı durum işte serbest particle oluyor. Yani yarı ömrünü tamamlamış oluyor. O kuyudan çıkmış oluyor. Bu bunun teorik formülasyonu.
Bir şey daha sormak var. Şimdi torium vardı, alfamız vardı.
Kur'an mı bu? Torium
Şey,
artı
uranyum
alfa
var.
bilmiyoruz. O istatistiksel bir süreç.
Tamam.
Uranyum var.
Tamam, uranyumumuz var.
Evet.
Uranyumda kaç tane alfa gruplarının serbest olduğunu bilmiyoruz. Aslında
İstatistik,
evet,
formülistik.
o serbestlik şu anda buradaki wave fonksiyonların çözümlenmesiyle oluşacak
Evet.
olan şeyler kenarda. Peki Claude Barrier'in anlatırken şey dediniz, işte düşük enerjilerde olursa yaralanma ömrü uzun oluyor, yüksek enerji.
Niye? Çünkü bakın şurada alfa olduğunu düşünün. Şurada alfa enerjisinin çok düşük olduğunu düşünün. Şurası enerji gibi düşünün. Q diyelim. Q diyelim. Tamam. Burada ise bunun siyah çizgiyle buradan buraya kadar. Yani yıllar olacak. Kararlı yani. Evet.
Peki şimdi aslında şu demek oluyor. Uranyum parçalanırken alfa atıyor ve yarılanma ömrü kısa olanlar gözlemlenebildiği için mi biz aslında işte parçalanması yani şeyi anlayamadım. Sonuçta alfanın enerjisi tek yani. Parçalanma
Kaç çekirdeğinde bir iş yok. Q. Q değerini hesaplıyorsunuz. Alfa yayınladığı zaman. Ona göre biliyorsunuz. Oradan mı?
ama her parça yani her her izotop uranyum için tek. Mi?
Evet, yani 238 için.
238 için tek.
Mesela. Evet. Bir değer biliyorsunuz.
Ha, bir değere sahip. Sizin oradaki o aslında aralık yani yaralanma ömrünün değişen aralığı kendiniz 10 particle.
2.
Tamam.
Ya bu mesela 237 olsaydı ne olurdu? İşte şu ona göre değişir. Onu demek istiyorum.
Tamam.
Buyurun.
Burada kullandığımız semboller, term simbollerin moleküler spektroskopiyle benzer olma sebebi tamamen dalga fonksiyonlarına ve
Evet.
isimlerle ilişkili.
Böyle, evet,
Elektronik
aynen.
katkı yok yani.
Tabii ki. Bu aslında atom fiziğinden borç alınıyor. Mesela tabii ki. Ama yani nükleerde biraz farklılıklar gösteriyor. Yani o farklar, ince farkları bildiğinizi düşünüyorum. Yoksa da tekrarlarım. Ama genel olarak tabii ki sembol olarak atom fiziği ya da moleküller olarak
Potansiyel değişik. Yani orada sende bir potansiyel var.
tabii orada nükleer potansiyel yok hocam bir kere. Atomik var vesaire. Dolayısıyla yani üç bölgeye ayırıp bu davranışları yani biliyorsunuz dalga fonksiyonu ve türevi bu sınır değerlerinde sürekli olmak zorundadır. Yani pisi 1 eşit olmak zorunda, pisi 2 o da eşit olmak yani nerede R eşittir A diyelim buraya. Ve bunun türevleri de tabii ki. O süreklilik şartlarından bu sefer orada enerji özdeğerini vesaire çıkarmış oluyoruz. Yani 3. sınıf kuantum fiziği ne kadar önemli? O basit kare koyu ya da bariyer, bakın şurada koyu bariyer birleşimi ne kadar güzel bir ama çok sofistike, çok zor bir problemi de çok basit bir şekilde çözebiliyor. 3. sınıf gördüğünüz kuantum fiziği. Evet, var mı başka? Devam ediyorum. Evet. Now, this is first derived by... Ha, buyurun. Yeah, please.
So we can see on the alpha particles which
Transmit.
are three alpha particles, right?
Yes, of course.
Okay.
Yeah, I mean, but this is a theoretical way of telling where the alpha particle is, what the energy is, how it behaves, and etc. This is, of course, is a kind of empirical approximation, but it works. I mean, like this is the gamma factor. Probably you already heard of it because you see, like imagine alpha, we are here, alpha particles, and we would like to get out of this door. Okay? Therefore, we are going hitting the door and coming back and hitting back, etc. That finally tunnel. This is like a kind of there is a frequency there, it's a period. From that one, we obtain this what is called gamma factor or barrier penetration formula. You see, this is exactly same as barrier tunneling problem of third year quantum physics. Exactly. Therefore, it is really important to know it theoretically. I mean, this is an example for you, like uranium, thorium plus alpha. Please have a look at it. Now, another concept you shouldn't know is spin and parity, of course. I mean, because there are forbidden states. I mean, sometimes it doesn't always decay because it is forbidden. Certain rules, conservations should be made. Therefore, this is called selection rule. In a equals 0 S state, for example, and alpha particle, 2 protons and 3 neutrons, depending on the power distribution principle, I mean, they have such configuration. And spin and parity 0 plus, okay? Now, imagine it decays from one level to another one. What is the rule? I mean, like, imagine from here to this one or that one. Would it be possible that this particle decays from that to here or that to ground state. What is the selection rule? That's called this selection rule. Therefore, depending on if initial and final states have the same parity, L must be even, or if the parities are different, L must be odd. Therefore, the possible states an alpha particle can decay is it is between J final minus J initial to J initial plus J final. Therefore, certain combinations are forbidden. For example, 0 plus to 1 plus decay is not possible, or 0 to minus is not possible. This is a conservation of parity, angular momentum, energy, mass, etc. Okay, therefore these are conserved findings. Now, second one is the beta decay. Beta minus, beta plus, there are two types of decays. And we observe these beta decays either at this neutron ridge, this is line of stability, value of stability here. These are neutron ridge region, proton ridge region, and alpha ridge region. Therefore, this is either through this way, beta minus, or that way, beta plus decays. Both are called beta decays. We know that from liquid drop model, we have volume term, we have surface term, plot term, and also Paris term. Therefore, now for all A, there is only one parabola for beta decay, whereas for even A, there are two parabolas. That means, for example, A for 121, there is only one stable liquid, whereas for 122, there are two stable liquid. This is called Z. If you take the derivative of this to depending on Z, you will find the Z minimum of that stable nuclei. Therefore, beta decay is in terms of is changing the Z value of nuclei. For beta minus, you see a nucleus change to another one. X changes to, for example, Y, or aluminum changes to silicon. With a electron plus antineutrino, or for positron decay, same with positron and neutrino. Therefore, why do we have this neutrino or antineutrino? It is because of the conservation of spin, actually. And for beta minus, you see here beryllium changes to bore. For beta plus, carbon changes to bore with electron and positron, neutrino and antineutrino. Q values are again delta n times c squared. And as you see, this is the Q value. It's when you have beta decay, when you have positron decay or beta plus decay. These are two processes, competing processes actually for beta decay. Please have a look at this for your case. I mean, from lithium to beryllium or lithium to beryllium excited state, you see here. Therefore, that one will go through the gamma decay to become stable, or oxygen to nitrogen. Yes, nitrogen. And mass excess there. Therefore, please calculate the Q values of such beta decays. These are important for diagnosis, actually. Mostly beta decays or positrons have been used for PET or even SPECT for diagnosis, but now recently for therapeutic cases, it is also used. Now, the beauty of beta decay is its decay, unlike the alpha, it is continuous. You see, if there was alpha here, it would be like peaked, like this. Discontinuity there will be, whereas here, for z equals 0, this one, that's beta minus, that's beta plus from up, and it is continuous. Therefore, beta decay is mostly used for the nuclear batteries studies, because it is like infinite energy sources at very small current value for space studies. Therefore, now the problem here is the calculation of Q value because of the neutrino. You see here, proton has 1/2 spin, neutron has 1/2, positron or electron has 1/2. Therefore, spin quantum number should be conserved. Whereas if you look at this side, without this, that's 1. The other side is 1/2. Therefore, Pauli suggested that there should be a kind of virtual particle with a half spin. That's called neutrino. So that this is to conserve the lepton numbers of or spin numbers of the or angular momentum conservation. That's called neutrino hypothesis. Now, the density of beta, the amount of beta particles are very important. I mean, because it is continuous spectrum, therefore the flux is very important. Therefore, the transition rate between initial and final states are given by Fermi's golden rule. That's a matrix element M, and the number of density of the particle, that's called this density of final states for the shape of beta spectrum, and this matrix element is the initial and final wave function normalization with the Hamiltonian. Therefore, this is Fermi's golden rule that's important for the flux. Same, I mean, there are selection rules for the beta transitions. If it is the total spin is 0, that's called Fermi transition. If it is 1, then it is called Gamow-Teller transitions. You should also know this. I mean, at least remember that there are different beta decays depending on the spin and angular momentum. Therefore, it should be Fermi or Gamow-Teller transitions because of the conservation of angular momentum and parity, as well as the properties of initial and final states. As you know, I mean, electron is a fermion with a spin 1/2 h bar. Therefore, it should obey the Pauli principle. Therefore, the parity also changes, and these are the, you see, allowed and forbidden transition states for different L values given. Therefore, this is for Fermi and Gamow-Teller transitions. These are important for future applications of electron or beta decay. Another competing process is the electron capture. I mean, it is mostly confused with the beta decay, but in this case, a nucleus captures the lowest, an electron from the lowest orbital, and it changes the structure. For example, AZ becomes a Z-1. Therefore, it is a kind of, in the beta decay, you are an electron was escaping, whereas in the electron capture, you are capturing an electron. These are two different competing processes, but the most important thing is the well-known. I mean, this is an experiment made by Wu et al. That's the parity violation in beta decay. Parity is not conserved. In some cases in beta decay, some details are given here. I mean, that's like something to do with helicity actually. When you know beta is moving like right-hand side like this or left-hand side like this. Therefore, parity tells you which way actually it is going. Whereas for alpha and other cases, while it is conserved, for beta decay, you cannot say that it is conserved all the time. Therefore, this is another important topic for beta decay. I have few more minutes. Finally, gamma decay. Gamma decay occurs all the time as long as nucleus is excited. When it is excited, it decays into ground state or any other state by viewing gammas, basically high energy photons, let's say. Therefore, this is also another decay process. It has a half-life, and finally you obtain a stable nuclei. Typically, I mean, the energy range is up to 10 MeV. Therefore, E equals h nu. Therefore, from there, you calculate the wavelength. It's up to 10 to the 4 to 150 meter. From the conservation of momentum and energy, you obtain the gamma transition energy easily by looking at the final and initial states. You obtain it, and the E gamma. Don't forget that the difference between the final and initial energy states. The transition rates, I mean, partial width, total width, half-life. Do you know all these some, or let me explain more? I mean, there is a resonance. I mean, when you look at this width concept, I mean, it is mostly related to actually resonances. When we look, what is the resonance? I mean, imagine you have a particle coming to another particle, projectile to target, for example. This A comes to this capital A or X, and it is scattered, and we observe through the detectors and count it as we obtain angular distribution, cross section, etc. Now, for theoretically, we reduce it to a reduced mass interacting with a potential field VR. This is the same. Now, if your energy is, this is Coulomb level, for example, or this one, if your incoming energy is very close to one of the energies of these excited states, then it resonates. Okay, the cross section becomes infinitely long. This is called resonance. Therefore, your incoming energy is very close to the energy levels of target, then it resonates. Resonances are observed. Therefore, there is a width there. I mean, what's called resonance width. And we know that width from Heisenberg answer to the principle, we know that there E, there E, H bar, X, there P, H bar. From this, we can use this to predict the half-life of that width or that resonance. Therefore, we predict the half-life of that particular case. And these are mostly, if they are living very long means 10 to the minus 5 seconds, then these are called isomeric states. Okay, these are a little bit advanced topic, but I will continue very fast. I mean, you see, when you have an electric, when you have a charge, you have electric field. When you move that charge, then you have electric plus magnetic field. Therefore, and particularly if they are very oblate shape and it rotates like the central mass, then you get these moments, multiple moments. It could be either electric or magnetic either. That is one of the hot topics of this field. This is called for phonons. It is L equals 1 dipole, quadrupole, octupole, hexadecapole, etc. These have all different shapes because of the coupling of angular momentums. You see, this is important topic, but little bit advanced. I mean, if you have any interest, please inform me so that I can repeat. Therefore, different multiple moments have different, of course, parity cases and also different shapes. Like it is called deformation length. Do you know, I mean, anything about deformation? Okay. Okay, it's like a coupling. You see, let me show you here very simply what I mean. And this is like, okay, this is like a angular momentum L. Okay, total angular momentum is L plus S. Okay, therefore S could couple to this one either up or down, because down is 1.5 h bar, because it's fermion. Up is 1.5 plus 1.5 h bar. Therefore, this couples to this one or that one, and it rotates like this, depending on M. What is M? Psi and Lm. M is minus L to plus L. To L plus 1, that means value. Therefore, it is like a coupling of two particles. That's called Gibbs-Gordon coefficient. Gibbs-Gordon coefficient. Therefore, two different states are combined and one state is obtained. That is called Gibbs-Gordon coefficients. Combine two different cases. Like this is the Legendre polynomial, as you know, and of course, spherical harmonics. And these have giving you these shapes, you see. Nuclei are like this. Don't think that these are spherical. Atoms also like this. Therefore, this is like for different M values, they have different orientations and shapes. Like one is just breathing, or the other one is like, you know, like this one, like Lundra, I don't know. Yeah, something like this. Okay. Therefore, these are living objects. These are not static. They are not staying like 200 neutrons are not staying there like that statically. They are moving and creating different modes. These are called electric or magnetic modes. And this is your imagination. This is all theoretical transformation, but these are reality. You see, they are really dynamic processes. And finally, I mean, these are very much used, alpha, beta, gammas, and neutron. Therefore, I stop here. We spent too much time today. I mean, 3 lectures in a row was very long, but I tried my best to tell you the basics of nuclear physics as a personal view. And if you have any questions, please don't hesitate to ask me now or later. Okay? Okay, thank you very much.